This is a perfectly elastic collision.
Okay.
Is it A minus L times A plus L?
It is. So this becomes MA, A minus L times A plus L is equal to MB Q minus B. Let's see if I can actually draw the letters that I'm saying. Q minus B, Q plus B. I'm going to factor the second equation now. Factor MA out, and I get A minus L is equal to MB Q minus B. Questions up to here? At this point, I have two equations. I'm now going to divide. I'm going to divide the left-hand sides and the right-hand sides. Again, the math people tell me that if I divide both sides by the same thing, it's valid math. And since those are equal to each other, dividing by the left-hand side by this and the right-hand side by this is valid. If A cancels out, A minus L cancels out, MB cancels out, Q minus B cancels out, and I'm left with A plus L is equal to Q plus B. I just probably should have kept that one, but oh well. We'll keep that version there. Putting back in terms of subscripts here, so I have VA initial plus VA final is equal to VB initial plus VB final. It's not the traditional way of doing it. This is the way that I remembered for years. Getting the initials together, I have VA initial minus VB initial is equal to VB final minus VA final. That's the more traditional way of writing it. This is known as the relative speed of approach. Yes, good. It's an error.
So where you start the white color,
Yep.
didn't you square root it?
No. Where would I square root it?
At the top, you went from MA A squared.
I factored MA out, and I'm left with MA times A squared minus L squared. And then
Oh, so
factor
that next part isn't valid in the white part? The MA minus MAL? Right.
This down here?
No, right above the white.
That. Right above the white.
That, yeah.
That is coming from the conservation of momentum.
Oh, okay.
And this is relative speed of recession. In this example here, from H's point of view, so if you're here observing it as opposed to from the lab frame, which is what we have here, if you're here, how fast does it look like 4 is coming at you?
Coming at you?
Yeah.
It doesn't look like it's coming at you, it just looks like it's standing still.
No,
No.
he was like.
If you're here at 8, how fast does it look like 4 is coming at you?
9.
Oh, if you are 8.
Yeah. That's just the difference between it. It's 10 minus 1. That's the relative speed of approach. After the collision, we figured out that this was -2 and this one was 7. The difference is 9. So from 8's point of view, it looks like force coming at it at 9 meters per second. And then after the collision, from 4's point of view, it looks like 8's going away at 9 meters per second. Solving it, we already know what the answer is, but we can solve it by taking, well, we have our conservation of momentum equation still, but now we have 10 minus 1 is equal to Q minus L. From this equation here, we have 12 is equal to L plus 2Q. From this equation here, we have 9 is equal to Q minus L. 2 equations, 2 unknowns, no quadratic involved. There are a slew of ways of solving this. Pick the one that you like the most, do it. Let's say if we solve for Q, Q is 9 plus L. Plug that in, and so I got 12 is equal to L plus 2 times 9 plus L. 12 is equal to L plus 18 plus 2L. 3L is equal to negative 6. L equals negative 2. And then plug it into here, Q would equal to 7, which is what we had before. Questions before I ask my question about this? My question is, when we solved it the first method, we had 2 answers, one of which was the non-collision solution. We solved it the second method, and we only got 1 answer, the collision solution. What happened to the non-collision solution? At what point did it just go away? There's something we did in the derivation which
The what?
eliminated it.
Oh, like derivative.
Yeah, because we didn't get L is equal to 10 and Q is equal to 1 doing it this method.
We canceled out the Q
No, that's not where
by
it's at.
substituting 9 plus L for Q. And so we just have Q. What the hell? Okay,
But if Q is 10 and L is 1, that would still be satisfied.
okay, so from 12 equals L plus 2Q.
Yep.
Then we substitute L, we substitute Q for 9 plus L. So now there's no Q, there's just L involved.
Right.
That's where.
But when we did this solution, we substituted in L is equal to 12 minus 2Q. And I mean, we still had 2 solutions.
Are you saying why on the next slide we only have 1 solution?
Yes.
Is it because, well, we factored out the a squared minus L squared, and then we were able to use the 2 equations and divide them from each other's both sides?
Why did that eliminate one of the solutions?
Because now there's only one factor.
Because it's
You canceled out. You see where the green is? How you canceled out?
Yep.
You divided the same thing by one of its factors. So you only have one factor left on each side.
But why does that eliminate the non-collision solution and not eliminate the actual answer?
Oh, it's because, wouldn't it just, am I lying? Oh, yeah, wouldn't it just because, wait, no. Because A minus L and Q minus B just equals 0, right?
I said earlier, math people say that I can divide both sides by the same thing, and it's legitimate. I actually did deliberately leave something off there, unless it's 0. You cannot divide by 0 because the math people haven't figured out how to do that yet. So, when I divided by A minus L, this is only valid if A does not equal L. If A equaled L, the non-collision solution, because A is the velocity of the first mass before the collision, L is the velocity after the collision. If A equaled L, this is not a legitimate step. So it's at that point right there, when I divided by this and this, that I eliminated the non-collision solution.
Yeah, can I ask a question?
Yeah.
Because I kind of got stuck at the second line of white. Yeah, there. Why is it A minus L times A plus L?
If you factor A squared minus L squared, you get A minus L, A plus L.
Wow, I must be having a migraine.
The difference of perfect squares.
Yeah, that's what it's called.
If you foiled A minus L times A plus L, you would end up back with this.
Fair.
Because the outer and inner term cancel out.
Okay, and then why did you divide it? Or how?
Well, from this equation right here, I factored out NA, so I factored NA out and I'm left with A minus L. Here,
Oh. So I really should have kept that written down then.
All right. So the advantage of this solution, or this method, is that there's no quadratic involved. The disadvantage is you don't get that immediate feedback that, hey, I've done something right, because we've eliminated the non-collision solution. So if you make a chaos error, it's not going to be as obvious. Questions about method 2 before I go over method 3?
Can you just stay on that side for a minute?
I really don't need this anymore. All right, so method 3. Let's just solve the one-dimensional, perfectly inelastic collision problem. So if we solve the perfectly inelastic collision, we had a total momentum beforehand of 48 is equal to, well, if they're perfectly inelastic, they're going to stick together, so my mass now is 12 times V final. And so V final is 4 meters per second. Dramatic pause for questions. We're just going to tuck that piece of information away in the back of our minds, maybe the middle of our minds for a little bit. All right, so observer velocity 0, velocity of 4, velocity of 8, P4, P8. All right, the observer going 0 meters per second, this is the lab frame or the problem frame. I generally refer to it as the lab frame. And in the problem frame, or in the lab frame, this is going 10 meters per second, this is going 1 meter per second. The momentum of the 4 kilogram mass is 40, the units are wrong there. Let's do Newton seconds, it's easier to write. And the momentum of the 8 is 8, and so the total is 48. This is just basically a recap. There's nothing different about this other than the way I'm presenting it. All right, so now we're going to observe the same problem, except we're going to shift the observer. The observer is now going 10 meters per second. So these are going those velocities in our lab frame. If I'm going 10 meters per second, well, it's positive, so to the right, how fast is the 4 kilogram mass going relative to me?
40 newtons per second.
Nope.
0.
Yes. It's at rest. If I'm moving that 10 meters, if I'm moving the same velocity it is in the same direction, it's going to look like it's at rest. So that would be 0. How fast will the 8 kilogram mass seem to be going relative to this observer? Yep. -9. So the momentum of the 4 kilogram mass will be 0 Newton seconds. The momentum of the 8 kilogram mass will be -72 Newton seconds, and the total is -72. And that should be Newton seconds. So I can shift what the momentum is just by changing the observer. But the physics should be valid regardless of what the observer is doing. If momentum is conserved in the rest frame or the lab frame, momentum should be conserved regardless of what I'm doing. I'm not affecting the actual physics involved there, I'm just affecting the numbers I use. Suppose I'm going 1 meter per second. How fast is the 4 kilogram mass going?
9.
So it's just that minus however fast the observer is going. So 9, this will be going 0. So that's 0, that is 36. So what we're going to do in the third method is we are going to shift our reference frame into a very convenient reference frame. I want to shift it into the 0 momentum frame. So I want this to be 0. Well, let's just do a little math. So when I shift to whatever speed it is, I'm just going to label that as v. This will be 10 minus v. This will be 1 minus v. This will be 4 times 10 minus v. And this will be 8 times 1 minus v.
Oh, that makes things so much more clear. I was so confused before now.
So we have 4 times 10 minus v plus 8 times 1 minus v is equal to 0. 40 minus 4v plus 8 minus 8v equals 0. 48 minus 12v equals 0. 48 equals 12v. v equals 4. I found the 0 momentum frame, but if the observer is going 4 meters per second, where do we see 4 meters per second before?
Velocity.
For what?
For perfectly inelastic collision?
Yes,
Only no stick.
and that is always the case. Because that 4 meters per second is actually how fast is the perfectly inelastic collision, that number right there is how fast the center of mass is moving.
Is that a big P or a little p? I can't. That's a little
Is
p.
that the last P I wrote?
No, the third and fourth. The first.
The P4 and the P8 are little p's.
Okay.
So when you're finding the zero momentum frame, you're looking for the velocity of the center of mass. And the velocity of the center of mass is always going to be the solution of the perfectly inelastic collision. So what I'm left with here is I've got my 4 kilogram mass. I have my 8 kilogram mass. So lab frame, this is going 10 and 1. That's the problem. My perfectly inelastic collision solution is 4 meters per second, so I'm now going to shift, and I shift by, well, subtracting 4 from each of them. And I have 6 and -3. So in the zero momentum frame, the 5 kilogram mass is going, or sorry, 8 kilogram mass is going to the left at 3 meters per second, and the 4 kilogram mass is going 6 meters per second to the right. We can double check. 6 times 4 should equal 3 times 8. And it does. Now there's a collision. I need a velocity, and I need velocities so that my kinetic energy stays the same and my momentum stays the same. This is my zero momentum frame. Should be a vector symbol somewhere. So, what is the solution?
Wait, so the momentum stays the same and what stays the same?
Kinetic energy stays the same. Where they actually collide. Remember, kinetic energy does not